Okay, so here are the examples of a Riemann sum. You want to find the area underneath the graph of sine of x from x is equal to 0 to x is equal to pi over 2 using 6 rectangles. So that means n is equal to 6 here. Okay? Now, we're going to go through and do the right endpoint, left endpoint, and midpoint method of finding these areas. And we're going to compare all of the values and see approximately what the answer is. So first, let's go ahead and try to draw a picture here. Let's find our delta x. Delta x is, let's see, this is my a, this is my b, so pi over 2 minus 0 divided by 6, that's pi over 12. So each interval is going to be a length of pi over 12. So let's see. Yeah, that's good. So this is pi over 2. This is going to be 1. Goes like that. And then if you recall, it goes down and then it goes up again. So this is the area of the this is the area that we're trying to find right here. Okay? The area underneath the curve above the x-axis between the lower bound and the upper bound. Now it wants us to do this using 6 rectangles. Okay? So do the best you can to look at it and figure out how to split this up into 6. Again, it doesn't have to be exactly perfect. There we go. I've got 1, 2, 3, 4, 5, 6 little intervals. Okay? Now, here's where you're going to decide on how to draw your rectangles. Either it's going to be a left endpoint approximation, a right endpoint approximation, or a midpoint approximation. Oh, first let's get these values here. So these little distances right here, right there, that's your delta x, which is pi over 12. So 0 plus pi over 12 is pi over 12. And then you could just keep going and adding pi over 12 to itself until you get to up to pi over 2. So it would be 2 pi over 12, which is pi over 6. And 3 pi over 12, which is pi over 4. Then 4 pi over 12, which is pi over 3. Then 5 pi over 12. And then 6 pi over 12, which is pi over 2. Now, since we are here, we're going to do a left endpoint approximation. All that means is when we draw our rectangles, what we're going to do, we split this number line up into 6 equal parts. This is going to be my rectangle, the base of my rectangle. I'm going to choose this left endpoint. I'm going to go up to the graph, and that's how I'm going to draw my rectangle. So here, at 0, I'm at 0. So this rectangle literally has no height at all. Now at pi over 12, for this interval, this next interval right here, between pi over 12 and pi over 6, I'm going to choose the left endpoint. I'm going to draw a line up to the graph, and I'm going to draw a rectangle like that. Then between pi over 6 and pi over 4, I'm going to choose the left endpoint, pi over 6, and yes, they will overlap. I'm going to draw it going up to the curve, and then I'm going to go over and draw my rectangle like that. and I'm going to repeat the process. Between these two, I choose the left endpoint, draw my rectangle. Between these two, I choose the left endpoint, I draw my rectangle. Between these two, I choose the left endpoint, and I draw my rectangle. So I've got all my rectangles drawn. Now, if it was a right endpoint approximation, instead of choosing the left endpoint, we're going to choose the right endpoint. And we're going to draw our rectangles like that. Midpoint approximation, you use the midpoint of the interval, and you draw your rectangles like that. Okay, just 3 different ways of approximating the area. Okay, so let's go ahead and get rid of some stuff. I want to keep my graph, keep my function. So, according to our area function that we had in the previous video, this should be equal to f of x1 delta x plus f of x2 delta x plus dot 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 plus f of x6 delta x. Where x1, x2, x3, so on and so on are the chosen points down here. What are the endpoints? I'm doing a left approximation. So for this one right here, I'm going to choose 0. Okay? Now, not only that, we know what our delta x is. Our delta x is pi over 12. This has delta x, this has delta x, this has delta x. You could factor a delta x out. So delta x times f of, well, my first left endpoint is 0, plus my second left endpoint is pi over 12, plus f of my third endpoint is pi over 6, plus my next endpoint is f of pi over 4. The next endpoint is plus f of pi over 3, plus the last endpoint, f of 5 pi over 12. Oh, I guess this should be a bracket. Now, what I would do is I would use your calculator to go ahead and input these values. You can calculate them by hand. You could do these ones by hand, but sine of pi over 12 is not on the unit circle, so you would have to use a calculator anyways. Let me go grab my calculator. I'll be right back. Okay, so I've got my calculator, and let's see, I'm typing this exactly in my calculator using the function value feature. You know of the function value feature if you watch my calculator tutorial videos for the Newton's method. So I'm going to type in y1, I'm going to type in sine of x. Okay, make sure your calculator's in radians as well. And now, delta x is pi over 12. I'm going to type in pi over 12. I put it in parentheses. And then I need another parenthesis. So you just open a parenthesis. I know it's a bracket here. And now f of 0. I can go to vars, y vars, function y1 of 0. Just like that. y1 of 0. And then I'm going to do that for every single piece right there. Okay? Plus vars, function, y vars, y1 of pi divided by 12 plus vars, y vars, function, y1, pi divided by 6, and you just keep on going. Pi divided by 3 plus 5 pi. think I messed up typing it in because I got a really big number. Let me type it in one more time. Pi divided by 12 times 0 plus one more. Okay, there we go. That's a lot better. I get 0.8633. Okay, 0.8633. Sorry for the delay. Now let's talk about this being an overestimate or an underestimate for our approximation. If you notice how we drew the rectangles, there is some area I didn't count here, some area I didn't count there. There, a little there, and there will be a little there. You just can't really see it because of the I'm freehanding it. So since I'm not counting some area, this should be an underestimate. Now, don't automatically think a left endpoint approximation is going to give you an underestimate. It can give you an overestimate as well. It just depends on the function itself. In this scenario, it just so happened the left endpoint gave you an underestimate, and when we do the right endpoint, it's going to give us an overestimate. Okay, so left endpoint approximation was 0.8633. Now let's go ahead and do a right point approximation. Now we could keep pretty much everything we have up here because it's going to look very similar. The only thing that's going to change here are these function values. So now when I'm looking at this interval and I want to do a right point approximation, get rid of that. If the endpoint I have to choose, I'm going to choose the one on the right and I'm going to draw my rectangle like that. As you can see, we're counting area above the graph, so this is the overestimate. So now out of these two, I'm going to pick this right endpoint. I'm going to draw my graph like that. And I'm just going to continue in the same manner, drawing these rectangles. And then you still do the approximation the same way. It's going to be f of x1. So the first endpoint, we're choosing the right endpoints now. This is the right endpoint approximation, so pi over 12. And we plug it into here. Then out of these two, we choose the right endpoint, which is pi over 6. We choose pi over 4. Then pi over 3, then 5 pi over 6, or sorry, over 12, not over 6, over 12, and then lastly, pi over 2. The delta x stayed the same. We're still going from 0 to pi over 2. We're still doing it with 6 rectangles, so this didn't change. The points that we're picking for our rectangles change. The heights of our rectangles change. If you notice right here, we have some area that we're counting that doesn't belong to the area underneath the curve. We should expect this to be an overestimate. So let's go ahead and plug this in and see what we get. This time it'll be a little bit quicker on my end. So you get 1.125. 1.125. So up our right endpoint approximation, a right endpoint area is 1.125. So we've gotten a lower bound for the area and an upper bound for the area. The area underneath this curve should be no less than 0.8633 and no more than 0.125. Okay? That's if we were able to find the actual area. Now, there's another method we can use. We did a left endpoint, we did a right endpoint. And I'll just redraw the curve. Let's go ahead and do a midpoint approximation. So for a midpoint approximation, what you do is you draw your rectangles based on the midpoint of the interval. Okay? So if I were to go ahead and find the midpoint of this interval right here, I'm going to draw my rectangle like that. Okay? Now the midpoint, to find the midpoint of an interval, what you can do is you could add the two values together, divide by 2. Okay? So 0 plus pi over 12 is pi over 12. Pi over 12 divided by 2. That value right there would be pi over 24. So to find the midpoint here, pi over 6 minus pi over 12. You could just leave the pi's out of it for a moment and just do the fractions. 1/6 minus 1/12. Turn that back into a fraction, and you get 1/12. Oh, I subtracted them. So you don't get 1/12. My mistake. You get 1/8. Or sorry, pi over 8. And then the next one would be pi over 4 minus pi over 6 divided by 2. And you get, let's see, the midpoint here. You go up to there. This midpoint is 5 pi over 24. Let's see, then you do the midpoint of this interval, and then the midpoint of this interval, and then the midpoint of this interval. Let's see, 1, 2, 3, 4, 5, 6. All right, so you just keep doing it. Let's see, finding the next midpoint would be pi over 3. So you do 1/3 plus 1/4 divided by 2. It gives you 7 pi over 24. Let's see, the next one would be 5 divided by 12. Plus 1/3. You get 3/8. So 1, 2, 3, 4, 5. Oh, I'm missing this last one right here. 1/2 plus 5 divided by 12 divided by 2. And you get 11 pi over 24. So the midpoint method can be a little bit of a pain just because now you have to calculate midpoints of the intervals. But if you think about it, it should be a little bit better approximation than the left endpoint or the right endpoint. So the left endpoint gave you a lower bound, the right endpoint gave you an upper bound. The midpoint method should give you somewhere in the middle between these two, closer to the actual answer itself. Okay, so all we have to do is erase our function values here. This one may come out to be an overestimate, may come out to be an underestimate. I'm not really sure. It depends on how you draw your rectangles with your midpoints, okay? Let's see, pi over 24, pi over 8, 5 pi over 24, 7 pi over 24, 3 pi over 8, and 11 pi over 24. So now let's go ahead and see what that gives us for our answer. So just typing this into my calculator right now. Just give me a moment. See, pi divided by 8, y of 5 pi over 24, y of 7 pi over 24, y of 3 pi over 8, and then lastly, f of 11 pi over 24. You hit enter. And if you look at that, 1.002. Okay, so this is the method on how to do it. Okay, your delta x stays the same, and all you have to do is either the left endpoint, right endpoint, or midpoint approximation and plug in your function values. Okay, now if we were to look at our results, we've got the left endpoint gave us a value of 0.8633. The midpoint approximation gave 1.002, and the right endpoint approximation gave us 1.125. So as you can see, the midpoint one, although we had to do a little bit more work finding those midpoints, was actually the best approximation that we had between the left, the right, and the midpoint. Now, of course, if you do more rectangles than 6, say you do 12 or 100 rectangles, so on and so on, they each will get better and better approximations to the actual area. In fact, the actual area is exactly equal to 1. The area of that curve right there is equal to 1. If you notice, look at the midpoint. It's really close to 1. Okay?